theorem A. So the theorem says that there exists a hyperbolic group which contains a subgroup which is of finite type that is not hyperbolic. Okay, so this means that being hyperbolic is not hereditary in any sense, unless you of course, if you add some other hypothesis, maybe it's hereditary. But if you add hypotheses that are only related to H and not to the way H is embedded in G, then it's not going to be hereditary. Of course, if you add hypothesis on how H is embedded in G, then it's not a story. But H itself is not going to guarantee you. So even if H is of finite type, it's not going to be a hereditary problem. So what does finite type mean? So finite type means there exists a finite a spherical W complex X with H. H is a fundamental group of a finite spherical CW complex. So for instance, it could be a fundamental group of a hyperbolic manifold, for instance. Okay, so some spherical finite CW complex. So this is the strongest possible finite assumption you can ask. So there was already some examples with finitely presented instead of finite type. So there is a famous example of greedy. So this was already a hint that maybe so you cannot achieve hyperbolicity by adding finiteness requirements. And the technique to prove this theorem is actually quite similar to the one used by Grady. It's always with this Grady theory. And actually this theorem is so it's going to be a corollary of another theorem. Theorem B. So there exists a hyperbolic manifold, the fibers over the circle. Here, when I say hyperbolic, I always mean finite volume and complete. Okay, these assumptions will always be there. Okay, and so how can you go from B to A? Okay, so how do you go from B to A? So there is a general thing about hyperbolic manifolds that if you want to construct examples, the cusped ones are easier to product. But if you want to prove theorems, the closed manifolds are easier to deal with. So I'm following this general thing. So although the manifold we construct are cusped, now in the proof I will suppose they're closed. Okay. So suppose M is closed. It is really a very general phenomenon. Okay, when you have to prove a theorem, it's better to suppose the manifold is closed. And then there is always a way to extend your proof from the closed to the cusped case, but you have to think about it later. So we start with the closed manifold, and if you have so the usual picture is the following. So every manifold that fibers over the circle has this picture. So you have a fiber F, and you can see the manifold. This is a 5-dimensional manifold as a product of a 4-dimensional one times S1 crosses the monodromy phi. And in monodromy is always interesting when the manifold is hyperbolic. So phi is certainly an interesting thing. So in particular, what we get here is that we take G, the fundamental group of M, and H, the fundamental group of the fiber. And we look at the monodromy. The monodromy is going to play a crucial role in the proof, because the point is that so hyperbolic manifolds do not like commuting elements in the fundamental group. So there is no Z times Z inside M. And from this one deduce that phi has infinite order in the outer automorphism group of the fiber. Okay. And this will lead you to a contradiction if you suppose that F is hyperbolic. Okay, because so suppose by contradiction that F is hyperbolic. Okay, suppose. And then you use Ripp's theory. Okay, so if you don't know what Ripp's theory is, you ask your neighbor. We certainly know better than me. The consequence of this fantastic theory that I use as a black box, okay, is that F splits over Z. This is not a contradiction in dimension 3, because as you see in dimension 3, the fiber is a surface. And the surface splits over Z because, for instance, the fundamental group splits over the fundamental group of this curve. It's not a problem. But in higher dimension, it is a problem because the fiber is aspherical. So whenever you have a bundle and the 3 objects are spherical and 2 of the 3 objects are spherical, the third one is also spherical. So since the circle is aspherical and the manifold is aspherical, the fiber is aspherical. And then you get a contradiction by hereditary. So you cannot have a closed aspherical form manifold was fundamental group splits over Z. It's not possible. It's just okay. So the reason for that is that here the H2 of the surface is Z because H1 of S1 is Z. But H4 of the manifold is Z and H3 of S1 is not Z. So this will give you a contradiction. Okay. So as a matter of fact, you get a contradiction by my hereditaries. Okay, so now that you have done the closed case, you can really think about the Casper case. So in the Casper case, if M is Casper, so luckily there are many papers on them filling. Okay, so in particular there is a theory of Fujiwara-Manning, which allows you to do some hyperbolic then filling in higher dimension. So in dimension 3, hyperbolic then filling means that if the curve is sufficiently long, then the manifold you get is hyperbolic. In higher dimension, this is not possible. So in higher dimension, what do you do? In higher dimension, you can do different kinds of then fillings, but the then filling that we want to do here is that we want to quotient every boundary component of the fiber to a point. So using this theory, you can quotient every boundary component of F. So F is a form manifold. So it's going to be, so typically the boundary of F will consist of a few number of 3 tori. So you can quotient every such 3 torus to a point. And in particular, every boundary component of M will be quotient to a circle. Okay, so you actually have the circles. So actually you get something like a fibration of a pseudo manifold where some circles have been added, and the fiber is going to be also pseudo manifold. But the point is that if the cusp section that you choose are sufficiently large, so if you choose cusp section where the systole is bigger than 2 pi, then everything you get is going to be hyperbolic in some sense. So in particular, so this is a theorem of Fujiwara and Manning. So if the systole of the cusp section you choose is sufficiently big, then this is not going to be a manifold, but it's going to be cut minus epsilon and Gromov hyperbolic. And this gives you all the ingredients that were needed here. You don't really need a true hyperbolic manifold. So because it's going to be aspherical, and also, I mean, all this theory also applies. Okay, so nothing really changes. So I'm talking about that. And you can achieve large cusp sections using residual finiteness. So the manifold you get maybe has some small cusp sections, but on some finite cover, at the price of getting many cusps. But it's okay. You get very large cusp sections. You can get thousands of cusp sections. It's not a problem.
So do you actually gain fill your fiber manifold, or do you gain fill some cover of it?
No, some cover. Yeah, to get to pi, some cover. Yeah. I mean, I haven't checked, but if the original manifold already has this system, I don't think so. I think you need it. Yeah. What have I done?
Transmitter gave out the part way through, so I've got to just swap it out.
Okay, thank you.
All right.
Okay, so the point now is to prove a theorem B. Okay, so there are 2 issues there. So, and they are both non-obvious. So the first one is to construct a hyperbolic manifold in dimension 5, and the other one is to find the fibration. Okay, they're both non-obvious in dimension higher than 3. Okay, and it's a lucky coincidence that the same objects work for both such tasks. And these objects are
right angle polytopes. Okay, so right angle polytopes, they do exist in higher dimension, and they are good both for constructing manifolds and for constructing fibrations. Okay, so because what is the point here? The point is that hyperbolic manifolds, finite volume and complete, they exist in all dimensions, even in dimension 1000. But the only technique we know in higher dimension, in very high dimensions, say bigger than 10. Okay, the only technique we know is arithmetic. Okay, so you build some arithmetic group, and then you use some arithmetic properties, and then you get some manifold, but you're not able to calculate anything, not even the first Betty number, the Euler characteristic when the dimension is even. So there's no way to calculate anything. Okay, the volume. Okay, so this is not a good technique if you want to construct a fibration. So if you're not even able to calculate the first Betty number, there's no chance you are going to find any topological construction. Okay, so the only thing that gives you some topology is the other way. So the other way is using Coxeter polyhedra. Okay, so if you use some Coxeter polyhedra, then you can see the topology. But among the Coxeter polyhedra, the simplest ones and the most powerful ones are by far the right-angled ones. Okay, because for them it's really possible to construct a manifold and to understand the topology, to compute Betty numbers, to see many submanifolds and to play with them. Okay, so these are the objects that we use. So we pick right angle. Okay, so the first thing to ask is, do they really exist? Okay, so because in the Euclidean world, we only have products of intervals, so only cubes, and it's quite boring. But in hyperbolic space, the situation is that right angle polytopes exist only up to certain dimension, like I don't know, 15. Okay, and then they do not exist anymore. But in low dimension, they do exist a lot. So in dimension 3, there are plenty of them because there is a theorem of Atelier that gives you plenty of examples. And in dimension 4, there are also many of them. We don't know how many, but there are. And also up to dimension 8, there are some examples. So in particular, there is a sequence of polytopes. P2, P3. So each of these is a polytope in a hyperbolic space. And when I say polytope, I always mean finite volume. Okay, so it's a convex hull of a finite volume of points in the compactification of Hn. So you can have ideal vertices. Actually, you must have ideal vertices. So one of the reasons for we are not able to build a closed example here is that there are no compact right angle polytopes in dimension 5. There are no. So this is a theorem. Okay, but there are right angle polytopes at least up to dimension 8 if you admit both ideal and real vertices. You need to admit both. Okay, so these are this type. So P2 is very easy to draw. It's just a triangle with 2 ideal vertices and 1 right angle vertex. Okay, this is the smallest right angle polygon in dimension 2. In dimension 3, you get this. So this is a bipyramid where these are finite and these are ideal. And this is also the simplest right angle polyhedron in dimension 3. Okay, you see both types of points arise. Simplest in both sense. It is probably the one with smallest volume, I think, and it's the one with simplest combination, the smallest number of faces. Okay, so probably in every dimension, these polyhedra are the simplest ones in both senses. I don't think this is proven for all dimensions, but for low dimension, it's probably okay. And then you go on. So this is a sequence. You see every face of P3 is actually isometric to P2. And then you go on. So P4 has 10 faces, each isometric to P3. And P5, which is the one we use, has 16 faces, each isometric to P4. So where do these magic polytope come from? So, okay, they come from a simple construction. Then it's not complicated. They come from the following construction. So you take a simplex. Suppose that you are lucky enough that in hyperbolic space, you have a simplex, which may have some ideal vertex, like for instance here, and such that there is a face which is right angle to all the others except a few ones where the angle is pi/4. So suppose that you have a face such that the angle of this face with all the others is always pi/2 except maybe one. which is pi over 4. Okay, so these simplexes exist up to dimension 8, just because they were classified in the 60s, I think by Wimberg, I don't know. Okay, so it's just this becomes classifying these simplexes become linear algebra. You find a Gram matrix. It's not terrible. Once you have this simplex, every time you have a Coxeter polyhedron and you lift it to universal cover Hn, you get a tessellation. So the space is beautifully tessellated by these polygons, and then you can take the star of this tessellation with respect to this vertex. So you're gonna get a polyhedron, like here, for instance, we get this. Okay, and this polyhedron will have only right angles, because the only angles that survive are these ones multiplied by 2. So pi 2 becomes pi, so and pi over 4 becomes pi over 2. That's okay. And then I think this was, so many people made this construction. So in particular, Potiagailo Wimberg and Ratcliffe Chance.
Where is that vertex in the three-dimensional?
Sorry?
The vertex that you drew, where is it in there?
So I think that here the small simplex is this one, and here you have to, I think this is the fundamental simplex. Okay. And the point is that now you can calculate the number of cusps. You can calculate everything just by using some reasonable formula. Okay. So you have this right angle polytope up to dimension 8. So okay. So now how can you use? Now the point is that how can we use the polytopes to construct a manifold and the fibration? Okay. So let's see how to construct a manifold. So if you look at the Coxeter diagrams, whenever you have a diagram which is like this, so some dots, and then you end with a dot, and then here like this is the simplex you're looking for, because this face is right angled with all the others, and is pi over 4 with this one. So you look at the tables, and you will find one such a thing in every dimension up to 8, and then you're happy. You say, "Hey, okay." It's not okay. Then, okay. So the way to go from polytopes to manifold is a technique which works only with right-angled ones, only with right-angled ones. I will be interested to find a similar thing with Coxeter polytopes, but I don't think there is one available. So it amounts at coloring the faces. And the first one who did this, I think it was Loebel in 1930, who constructed the first closed hyperbolic tree manifold, starting with the right-angled dodecahedron. Okay, so he used a different language, but as far as I know, this language is actually the same thing I'm going to explain. Okay, so he started with the right-angled dodecahedron, and then he wanted to construct a hyperbolic tree manifold which is tessellated in a certain number of this dodecahedron. So the thing you do is the following: you start with your right-angled polytope, and then you pick a palette of colors like numbers 1, okay, and then you add you color faces with numbers in such a way that adjacent faces get distinct numbers. Okay, so these two are not adjacent because this vertex does not exist. Okay, and then what you do is that you mirror your polytope along the faces with the same color in any order. The result will be independent of the ordering. So for instance, if you start here, you first mirror along the face 2, and then you get this. Okay, you get an ideal triangle. Okay, and then you mirror along 1 simultaneously, and then you get a trispunctured sphere, and that's all. Okay, there are more. There are finer versions of this construction, but we don't need them. Where you put some vectors here in some vector space, but we don't really need them here. So there is you can choose the trivial coloring. Inefficient, let's call it the inefficient coloring. The inefficient coloring is the one where every face gets a different, so you take k equal to the number of faces, and you give all the colorings to all the faces, all the colorings. Okay, so this one will produce a manifold which is also constructed in other ways. Okay, so it's the manifold that you get by taking the abelianization of the Coxeter group. It's also a manifold constructed with a technique which is called these manifolds are called real moment angle manifolds. They are connected to the Davis tree, and so everything is connected. And so you get, so when you, So there are many ways to see the same thing. Okay, so it's right. And if you use another coloring, you actually get a quotient of this manifold. Okay, so if you already know this manifold, then the manifold I'm using are quotients of this. Okay, I call it inefficient because, for instance, if you start with P8, which has 240 faces, which correspond to the smallest elements in the A8 lattice. Okay, and you know this inefficient coloring with 240 colors, you get a fantastic 8-dimensional manifolds whose number of cusps is close to the number of atoms in the visible universe. Okay, so you probably want to look to, so here you can color this polytope with 15. I don't remember whether it's 15 or 16, a reasonable number of colors. Okay, you don't really need to do this. Okay, it's when you construct higher dimensional hyperbolic manifolds, you sometimes encounter the fact that numbers are big and you get very big numbers of everything, big Betty numbers. Okay, so you should try to avoid this. Is there any question? Okay, so for instance, I show some examples. Okay, we did this one. So for instance, we can take this, or we can take the right angle octahedron. So this one can be colored with 3 colors. This can be C also because you can take the dual polyhedron. The dual polyhedron is a prism. You have just to color the vertices of the prism. You put 1, 1, 2, 2, 3, 3. Okay, so this can be 3 colored. This can be 2 colored. Actually, you can put white, black, and go on.
What are the rules for what colors are allowed to be next to each other?
So you faces that do not intersect can have the same color, and the ideal vertices do not exist. So these 2 faces can have the same color because this vertex does not exist. So it's, you can see from the diagram here. Here you get a cube as a dual object. Okay, and then of course there is the obvious coloring. Okay, so for instance, if you use this coloring, here you have 6 ideal vertices. Okay, so the octahedron, the right angle ideal octahedron has 8 ideal vertices. And so what you get, so since you have 2 colors, you get a manifold which will be tessellated into 4 copies of this, because if you have k colors, you get a tessellation to the k copies of the polytope. So you have a manifold tessellated into 4 copies of it. Above every ideal vertex, you have some cusps, maybe more than 1. In this case, only 1. And here the manifold you get is the complement of the minimally twisted chain link with 6 components. I don't draw the crossing, it's the minimally twisted chain link. And here you get the Borromean ring. Okay, so I mean, you get reasonable manifolds. Okay, so in particular, P5 has 16 facets. So all these polytopes from P3 to P8, they are extremely symmetric. Okay, they are dual to some polytopes discovered in 1900 by Gosset and called Gosset polytopes. They're extremely symmetric. Also because the quotient is a simplex. By construction, they are symmetric because you start from a simplex and then you expand. This means that the isometry group will quotient the polytope back to the simplex. So they have many symmetries, and this enables you to find some nice coloring. So in particular, this one has 16 faces and can be colored with 8 colors. And then you get a manifold that we call M5. Okay. And you can analyze things about this manifold. Okay. So now let's go to the fibration. So in dimension 4, you can also construct compact examples with this technique because you have the compact right angle 120 cell. In dimension 5, there is no compact polytope, compact right angle polytope. So the best you can do is to use this one, which is the only known right angle polytope in dimension 5. Of course, if you have one, you have infinitely many because you can reflect it along faces, but it does not produce anything more interesting than P5. Okay, so now how do we construct the fibration? Okay, so there are two ways to do this. So the first one is the one we used, and which is written in the paper we wrote, and it's via Besvina-Brady theory. And there is also everything comes from a crucial paper written 5 years ago by Yankiewicz. No, Yankiewicz, Norin, and Wise. And I'm going to talk about this. And there is also a second way to see this vibration, and this is maybe something new, which is similar to what Thurston did. Okay, so since you already know what Besvina-Brady theory, I think I will have the time to sketch both approaches. Okay, so the first thing to note is the following. So whenever you have a manifold which is tessellated into right angle objects of any kind, like hexagons, for instance. So whenever you have a manifold like this, dually you have a cubulation. This is always true. Okay, so a manifold tessellated into right angle objects has a dual decomposition, which is the composition into cubes. You get cubes because you get right angles. Okay, so here you get squares, for instance. And this is true in all dimensions. So in particular, the manifold M5 is tessellated into some copies of P5, and dually you have a cube complex C. When the manifold is cusped, the cube complex is a spine of the manifold, because the cube complex is compact, finite, so you cannot cover all the manifold. So the manifold collapses onto the cube complex if M is cusped. Okay, so there are some colors to be added to the cube complex. Okay, and then you can try to use this cube complex to construct a map from your manifold to the circle, which I will see as this quotient. And one way to do it is the following. Suppose that you are able to orient every edge. Suppose you're able to orient every edge of the cubulation. Okay, in a way that every square is oriented coherently in this way. So every pair of opposite edges have the same orientation. Then if you are able to do this, you get a map. Because you identify every cube, so these arrows gives you a way to identify every cube canonically with the standard cube in Rn. So this is the standard cube. You put the origin in the origin of the arrows, and then you take this map, which this is called the diagonal map. The fiber of this map is something, so it's made of triangles and then hexagons and then triangles and then you go on, and that's Besvina-Brady theory, right? So you can then you analyze at every vertex the ascending and descending links, and if they are both contractible, then you can smoothen this to a vibration. Okay, so a theorem. No, I will write it there. I'm not stating precisely, but so yeah, what do I exactly? That's why I'm not stating it precisely. If all the ascending and descending links are collapsible. So collapsible is more than contractible. So we are in PL. We strongly live in the pi-Swiss linear world. Okay, which is up to dimension 5. It's okay because it's like smooth. Okay, and collapsible means it should collapse to a point. And the same thing occurs at the cusps. Okay, then you get a vibration. So because F is actually not defined yet. So F is defined on the cube complex, and which is only a subset of M. So it's not really a map from M. Moreover, it's not smooth. So the map is not smooth. So there are some problems. So the map is PL, is not smooth, and it's not defined everywhere. But smoothness can be achieved. Okay. Smoothness can be achieved, and moreover, same thing at the cusp means that the cusps inherit also cubulation, and and the same condition must hold at every cusp. So at every cusp you get a restricted function, and you must have the same condition. Okay. So then you can you can promote F, you can extend the F from C to M, and you can smoothen, so you can promote F to a fibration. Okay, I'll show an example. No, I don't show an example because I need the, okay, so, okay, how can we find these arrows? So this is where the paper of Yankiewicz, Norrie, and Wise come from. So there is a combinatorial game that you can play. And so the combinatorial game goes as follows. You start, so the cubulation you get is very symmetric. There's lots of symmetries. Actually, all vertices of the cubulation look the same, because the point is that every vertex of the cubulation corresponds to a polytope. And these polytopes, they're all obtained one from the other by mirroring. So the isometry group of the manifold acts transitively on the polytopes, and in particular on the vertices of the cubulation. So all these vertices have the same link. Okay, it's a very symmetric cubulation. So the idea is that you look only at one vertex and you fix the arrows at this vertex, and then you extend somehow canonically. Okay, this is the idea of this, and I will explain this better. So I will explain this directly with this example here. Okay, this example is nice because there are only two colors. So actually, so this implies there are only 4 octahedra. And I drew the duals of the 4 octahedra. So one is already there. Okay, so these are the duals of the 4 octahedra. And these are the links of the 4 vertices in the cube complex, which is dual to this decomposition of octahedra. Okay, so the point is that these are the links that you have to check when you do Bezzini-Brady theory. Okay, when you do Bezzini-Brady theory, you have the links, you have some links, and you have to check this ascending and descending links condition. So what you do is the following. So you start, so here, so this cube is dual to this. Okay, the numbers are not important anymore. So this cube is dual to this, and now so this is the link of a point. So this you can think about the central point, and there are some edges. So every point corresponds to an edge exiting from this point. So there are 2 possibilities. You want to put an arrow of this edge. Either it goes outward or inward. So you write O, 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 E. Okay, you choose some O, E, E, E. Dually on the faces, this means that you have O on this face, and then O, and then O, and then E. Okay, this means somehow that your function will be increasing when you cross this face, and decreasing when you cross this one. Okay, do you get the picture? So, okay, so this is the link. This is a link. So every time you have a cube complex and you take a link of a point, and if you add some labels like O and I, you are telling whether the arrows starting from that vertex are pointing outward or inward. This is what you do. Okay. Now that you have done this for one octahedron, now you must extend this coherently. And to extend this coherently, you build some moves. A system of moves that allow you to extend these arrows from the edges that start from the point dual to this octahedron to the other edges. Of course, something is needed. For instance, whenever you cross a face here, if you cross one face, if it was O, it must become I. No, because you have an edge. So whenever you have an edge going from one vertex to the other, of course, this edge here, if you look at the link here, this edge here is marked with an O. And if you go to this other link, so the same edges should be marked with an I necessarily, otherwise it doesn't make sense. Okay. So for instance, here as a move, you can take this one. So whenever you go from one cube to the other, you switch this, we call this the state. So we switch the state of all the points that have the corresponding color. Okay, it's because you go from this octahedron to this one by mirroring along the, let's call it the black color. Okay, and we go from this octahedron to this one by mirroring along the white color. Okay, so here you go from here to there by crossing a black face, and you go from here to there by crossing a white face. Okay, and these vertices are black and white. So, for instance, as an admissible rule, you can choose to switch all the states of the black points. So this means, for instance, that here I should modify 0, 1, 0, 1, and then you get, yeah, should modify these ones, right? So 1, 2, 3, 4. So this I, O, and O, and these remain the same. Okay, so I mean, this is just a rule, and here you get the opposite of this, and here you get the opposite of that. Okay, so I mean, if you're confused, it's not a problem. So you get, so there are certain rules that you may fix. Okay, you fix some rule to. So the idea is that you pick only one vertex of the cube complex. You decide which edges are inward and which are outward, and then you fix some rules that propagate all these arrows everywhere. Okay. Another thing to check is that every link should be every ascending and descending link should be collapsible, and this is true in this case because you see, for instance, if you take the link with the ascending link is this one. Okay, this collapses to a point, and this is also the descending link. It also collapses to a point, and you get a similar picture in every cube. So in particular, in this way, we obtain a fibration on this hyperbolic three-manifold, which is a complement of the chain link. Okay. Okay. So, and the idea is to do the same thing with P5 with some small modifications. Some small modification is that we also allow things like this. Okay, so these were not allowed. No, I only wanted things like this. Well, we should allow this. So we need. So if you allow this kind of arrows, then you subdivide the cube, and then you still have a Brian Brady theory with some subdivided cubes. So you add more vertices. So things get a bit more complicated because you get Brian Brady theory on a subdivision of a 4-dimensional cube complex. But then you have to check that every vertex, the ascending and link condition, that this condition holds. Okay, and this is true. So this holds because the polytope is so symmetric that you at some point you guess a solution of this problem. Okay, there's no deep reason for that. Do you have any question? Okay, so I have time to talk about the second method. Okay, so now this is another way to see the same construction. So there is a fantastic description of Thurston of so in my opinion the simplest example of a fiber enclosed hyperbolic three-manifold. Okay, so as I told you, closed examples are more difficult to produce, but with this exception. Okay, this one is closed and it's very, very simple. So you start with the cube and then you subdivide the faces in this way. Okay, and then you identify opposite faces of the cube to get a tritorus. And the tritorus contains a link because every such curve closes to actually it's a flat tritorus which contains some three geodesics. So these are geodesics. And actually, if you do the tritorus minus L, you get something which is homomorphic to the complement of the Borromean rings. Although we will not need this, but it's nice. And now what you do is the following: you interpret this cube as a dodecahedron. So this cube has. If you think about cutting every square in two, combinatorially, you get a polyhedron with 12 faces. They are all pentagons, so it's going to be a dodecahedron. Okay, so if you interpret this as a dodecahedron, you can do the following. You can take a right-angled dodecahedron. So you interpret this as a right-angled dodecahedron instead of a cube. So the angle here is going to be pi over 2 instead of pi. All the other angles will be the same. That's important. So it's like we modify only the angles of these edges. And you can do this if you want. We don't really need this, but you can do this by deformation. You can think that this cube is an infinitesimal Euclidean cube, and then you expand it in hyperbolic space by making this angle smaller and smaller until you get pi over 2 and you're happy. Okay. And now you interpret the same thing, and you don't get a flat three torus. You get a hyperbolic three torus, which is of course impossible, but with a singular set. So L is going to be a link where the cone angle is pi, because we have only two dodecahedra meeting at this knot, not four. Okay, so actually this pair, this is a hyperbolic orbifold. Okay, so we get a hyperbolic orbifold. We can call it a pi orbifold or a two orbifold. So these are the simplest kind of orbifold. Pi orbifold means an orbifold where the only singularity has cone angle pi. So the only non-trivial local group is generated by a rotation, pi rotation. Okay. And now, where does the fibration come from? Oh, this is also a very simple way to construct a manifold. So if you want to construct a closed hyperbolic three manifold, this is probably the simplest way I know. Okay. And you can also get the fibration because you can, so you take, if you look at the usual affine fibration of the torus, there are infinitely many of them. There are three of them that are not good, this one, and this one. But all the others, they are transverse to these curves. All the others are good. In particular, the diagonal one is good, which is connected to the thing we saw before. So, and this fibration lift to any manifold cover of this. So this object has many manifold covers. And this fibration of the orbifold lifts to a genuine fibration of the manifold, where the fiber is going to be a branched covering over the fiber of this. So the fiber of this is a torus with 3 points. Okay. Okay, so a similar technique works in dimension 5 with some smaller adjustment. So to jump to dimension 5, we first make a first jump where we go from closed to cusped, and it goes as follows. So you consider this link. Okay, so this is a sketch of a link inside. So this is a link inside torus times R. Okay, so you have a torus. So this is a torus. Then inside this product, you take a link. And what I'm saying is that in this case also, this is a hyperbolic pi orbifold. This is also hyperbolic pi orbifold. And the only difference is that now we have cusps, because you have T times R, which contains a link, and there are two cusps. T times plus infinity and T times minus infinity. Okay, with two cusps. The construction is the same because you can see this by taking a cube, maybe a bigger cube. So you take a cube and you make something similar to what we did here. So we do something like this. Okay, so now consider this cube with these faces cut in two in a non-straight way. So everything. And now you cannot identify opposite faces because they don't match. So actually what we do the coloring thing. So we reflect first along these faces, and then along these faces, and then along these faces. And then we get a three torus. So no, not this one. This one we leave them, sorry. We reflect along this, and then along this. And then we get a torus times R, tessellated into 4 copies of this cube. 1, 1, 1, and 1, okay? And the link is going to be this one. So these curves, they will make a bridge, like you go here and then you go here, and that's the bridge we have here. So okay, so this is a way to construct topologically this picture, and this also by a theorem of Andreev can be realized as a right-angle polyhedron with these two faces removed. Okay, so you should think of, so an ideal polyhedron is a polyhedron where we remove some vertex, but it's also, we are also allowed to remove a face. So you remove this face and this face, or if you prefer, you shrink the face to a point and then you remove the point. It's the same, but I'm not able to draw the picture. Okay, so you remove these two faces, and then the resulting object will have a right angle structure with a right angle here, 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 everywhere. So it's going to be exactly like that, and you get this picture. Okay. Okay, so this is the picture that generalizes in dimension 5. And maybe I can tell you a story. So this example is quite famous, and some people try to generalize it to higher dimension. Okay, so there is in the famous paper of Gromov, there's an attempt, which didn't work, but nevertheless, it's interesting. So you start with the 5 torus, okay, and you take many parallel copies, many copies of 3 tori in it. Okay, it's the same. It's like here. You have the 3 torus and you have 1 tori. Okay, so codimension 2 objects. But in the 5 torus, the 3-dimensional tori will intersect into circles. And then you take the branched covering over this object. Okay, this will have a cut 0 structure, but it's not going to be hyperbolic. Okay, so it's not possible to generalize this example to dimension 5 as is. So it's not going to give a hyperbolic object. Okay, that's the point. So what is the difference here? So the difference here is that it's going to be slightly more complicated. So I'm going to finish with the theorem. So the point is that, yeah, what is the point? So the point is that P5 looks like this. So P5 has 16 faces, and this combinatorial equivalent. So what is this picture? This picture is a 2-dimensional cube times R. So these 2 faces do not exist. It's just times, so a 2 cube times R. And here we get a 4 cube times R. Okay. So if you look at this polyhedron, this infinite polyhedron, it has 8 faces because this is a 4 cube. So if you subdivide every face in 2, you get 16. Okay. So this right angle hyperbolic polyhedron in dimension 5 is exactly like this. So it's combinatorially equivalent to a 4-dimensional cube times R with all the vertical faces subdivided carefully in 2 so that they become 16. Okay. And then you remove some faces. So after removing, so the crucial point here is that we don't care about ideal points. So P5 has a certain number, has 10 ideal vertices. And the object we get here is going to have 2 ideal faces that will be removed and also 8 ideal edges that will be removed. So the point is that, so when you have an ideal polyhedron, you can consider an ideal polyhedron, as I said before, as a polyhedron where you remove some faces because you consider them at infinity. So combinatorially, it's like a subdivided cube. So P5 is more or less like a subdivided cube. And so the same construction of Thurston applies because it applies also here. I didn't say that, but here you can take a fibration of the torus of this one, a diagonal one. So you take a fibration where the fibers are like this, and the fiber will be transverse to the set, and then you will get a fibration of on every manifold that covers this orbifold. Okay, so the construction of Thurston applies also here because you have a torus. Whenever you have a torus, you have many fibrations. Okay, and so in dimension 5, the same thing happens. Okay, so in particular, I can state a theorem and then I stop.
Above this slope, by the way.
Yeah, so we are ahead.
So yeah.
Yeah. Okay. So I think I can just avoid stating any theorem. Okay. I think it's fine. Okay. Thank you.
What theorem were you going to do?
Sorry.
The theorem.
What theorem?
Yeah, that's
Yeah. No. The theorem is. The theorem is that, so it's like this. So there is an hyperbolic pi-orbifold structure on something like this. So this is a hyperbolic pi-orbifold structure on something which is a torus with a link, but now it's going to be 5-dimensional. So it's on the 4 torus times R minus some points and the link. Okay, so the point is building a hyperbolic orbifold structure or something which looks like a torus, and then the torus fibers and the fiber lifts to the manifold. Okay, this is what works. So in particular, this works here with this 5-dimensional object. You remove 8 points, and this will create cusps. You get 10 cusps, 2 from here and 8 from here, and the link is going to be codimension 2. So the link. Now you remove 8 circles. Sorry. 8 circles. Okay, so it's 4-dimensional torus times R, so you get 2 cusps. Then you remove 8 circles and get 8 more cusps. And then you get a link, and the link is going to be a 3-dimensional thing. So it's going to be 8 copies of the complement of the Borromean rings. So the singular set needs to be hyperbolic. because whenever you have a pi orbifold, the singular set inherits a hyperbolic structure. So that's the 5 manifold. These are the cusps, and the singular set is a 3 manifold, and which goes to the cusps. Okay, so the circles are here. So okay, and this yeah, and this and the picture is like here. So the singular set is almost horizontal. So it's horizontal only up to some bridges. And this implies that for most vibrations, it is transverse to them. Okay, this is just a picture. Okay, that's all.
Your vibration is one of those vibrations.
Yeah. It's just a different way to construct the same vibration.
And is your manifold a double fold cover?
Then you can, yes, it's up to commensurability. It's always the same thing. You can play, and it's always in the same commensurability class. Yeah.
So I think in the interest of time, we'll leave further questions to the break.
Yeah, sorry.